Hi there, welcome back to the channel, and welcome to the 6th video in the restoration of the SABA Meersburg 100. In this video I'm going to handle the FM IF alignment as well as the motor alignment for the FM. And this radio presents rather an interesting quirk in that the IF for the FM is not the usual 10.7 megahertz, it's 6.75 megahertz, which is not usual. It's not unique, but it's certainly not usual. If you go and look at some of the reference material online, you'll find there are actually quite a few radios that use that, but obviously the 10.7 is the most common one. Now, having completed the AM bands, I wanted to do the FM, and that's what I'm going to tackle here. What I wanted to do was actually measure the result of the alignment that I do. So I went old school. I did a plot of the existing passband of the FM IF and literally plotted it on a curve. I then did an alignment by the book. In other words, following the instructions exactly as they give it to us. And I plotted that response, which is a little surprising, not what I expected. And then finally, I tackled a visual alignment, which certainly makes the whole thing a lot more intuitive and a lot more precise and a lot more manageable. So this video is going to show you all that, show you all those stages, and also show you a trick on how to do the visual alignment accurately. Because we've got capacitors in there that certainly affect the curve, this video will show you all that. So if you're into that sort of thing, stick around and enjoy the video. But before we carry on, I just want to thank the sponsors of the video, PCBWay.com. They're running their 9th anniversary promotion at the moment. And this is an opportunity for you to get masses of free coupons. Go to the website, have a look around. There's coupons for orders over a certain amount for certain types of orders. They're running an anniversary sale as well on PCB prototypes, assembly, advanced and flex rigid PCBs, discounts on 3D printing and CNC machining. And there's also the unboxing of blind boxes. Some pretty good prizes on here. You can also then visit the PCBWay store where you can get a lot of products and modules that'll just complete your workshop. So visit PCBWay.com. I'm sure you'll find something for you. As you can see, I've got a lot of stuff stuck into that socket down there, so I'm ready to do some alignment work. Now, this time I'm going to do the FM alignment, the IF alignment, and the motor alignment. And I'm following the instructions, and the first thing you notice is that things are a little bit different here. This is normal. There's a drawing on there and tells you exactly how to do this. What you're measuring here is really the voltage between that ratio detector capacitor. That's fine, no big deal. And then you've got two resistors on there. 200k each. This is actually 220. I've matched them very carefully to within 0.1% or something. And you put a microammeter between point Z and the junction of those two resistors. It's all very well described on most of these service manuals for the SABAs. But the difference here is actually the IF frequency. That is not a mistake. This thing has got an IF frequency for the FM, which is completely different to any of the ones I've done before. Usually you see 10.7. This thing is 6.75 megahertz. You heard me right, 6.75 megahertz. It is different from the previous versions that I've done. It's different from the following versions that I've done. So the, the W3, the Meersburg W3s were 10.7. The Freiburg W2 was 10.7. The Willingens that I did were 10.7. The Breisgau, this one, 6.75. Now, that's fine because it is, it's more than half of the spread of the FM that you're trying to reach. You can go and read that up. There's actually a pretty good explanation on the web for that. Some radios did use this. I think this is probably one of the only SABA series that does. Now, what I've got here is the voltmeter set up across X and Y to measure the voltage across the capacitor. And it's set to 10 volts. I think we'll reach about halfway. The microammeter is there to measure the deflection. It's set in the middle at the moment. So we're going to measure the deflection to balance the ratio detector. And there's one other thing that's a little bit unusual on this. You see, on most of the FM front ends, you have one tube. Usually it's the ECC85, on the German radio front ends at least. This one's got two. It's got two EC92s. Now, the ECC85's got two triodes inside. This is a single triode each. So what they've done is they've separated the RF front-end amplifier from the mixer oscillator, and they've given it a tube each. It does help. I've mentioned this before. Now, most of the SABAs that I've done are like that. I think all of them are like that. But it means that you don't actually couple it the way you normally do. Usually what you do is you couple it to lightly across or over the ECC85. I use like a self-wound coil. You flip it over the top, you put the signal on there, and it couples lightly to the tube itself, and it gets through the IF chain. This one tells you to do it slightly different. It tells you to connect it to the bottom end of a particular trimmer capacitor, and that capacitor is actually down here. And you think, well, how the hell are we going to get there? Well, the bottom end of the capacitor, one side of the capacitor is actually the screw, the thread, which you then use to trim, and we'll be using that to adjust later. And it's pretty visible. You can see it through the top there. So I'll take the signal with a croc clip and just make sure I don't touch anything else. Clip it onto the screw itself. It's quite a big screw. And the other side of the signal generator can just go to the chassis. And we've got it done. Okay, so far so good. Let me show you what they tell us to do. We're back to the instructions here. We've got the instructions for the AM. And there's obviously the RF for the AM, which I'll do later when I've got the glass in. But then it tells us that we get to the FM alignment. And again, this is quite easy to follow because I've got the English instructions for the 125, and it's very easy to correlate between one and the other. But again, they tell us to select FM, fine. They tell us to switch the automatic off, fine. Then they've got this drawing here, and they tell us to connect a voltmeter with input impedance of greater than half a meg, which is the same story as before, 10 volt range, to the sockets X and Y. Now, Y we know is ground, so it's between X and Y. And there's our voltmeter. There's X, and there's Y. I'll show you where X is in a second. And then they tell us to connect a microammeter with a center 0 between X, Y, and Z. Now, what does this mean? Well, you take two 200K resistors. In my case, I've got 220. It's not a problem. They can be different values or close to 200, but different values, as long as they're very close one to each other, one to the other. So I've matched two resistors. You connect that to X and Y as well. And then you join those two together at the top, and you connect your microammeter between that joint, that junction, and point Z on there. Now let me show you what it is we're doing. We can go to the schematic. And if we look at this section here, which is what we're dealing with, when they tell us to connect the voltmeter between X and Y, what we're doing, Y is chassis ground, remember? And we're measuring the voltage across that ratio detector capacitor. So there's Y, that's ground, and the positive, or rather in this case, the negative voltage, so it's the negative of the capacitor, is point X. So we're doing this as we usually do. This is the usual thing. You measure the voltage across that capacitor. So that's for the voltage measurement. And you're going to peak all the IF transformers till you get a maximum voltage on there, with the exception of the last one. So the last one, you're measuring between X, Y, and Z. And what you're doing is you're taking a resistor from this point here to ground through another resistor. So 100K or 200K, joint 200K to ground. You connect to that joint and you connect to this point here. This point is where your audio comes out. But what you're trying to do is to adjust it so that the midpoint between these 2 points over here, which is what you'll get when you connect to the junction of those two resistors, and this point here are perfectly phased out. So you get zero current flowing or zero voltage. So that's what we're doing here. It's not unusual. I've done this before on other radios, even without the sockets. You just need to know what you're looking for. But that's what we're doing over here. And what we're going to do is we're going to do the usual thing with these cores. And here they tell us to send a 6.75 megahertz unmodulated signal through a capacitor. I've got my switch there's got a capacitor in between, to capacitor 105, to the bottom end of capacitor 105 and ground. Capacitor 105 is detuned till you get no noise in the voltmeter. What are they telling us to do here? Again, if you look at the schematic, makes sense. See, capacitor 105 is over here. The bottom end is this guy over here. When they tell us to detune 105 first, to get rid of the noise, what they're telling us to do is to detune this circuit here, this tank circuit over here, which takes the front end. Whatever signal's coming in here gets amplified by this triode, and it gets generated the voltage, that signal gets generated across this coil, and that then goes to the grid of that triode, which serves as a mixer oscillator. But what we're doing is we're detuning this whole thing here so that no noise, or as little noise as possible, comes from the front end over here, so it doesn't interfere with your with the procedure. And by connecting to this point over here, it's convenient because it's actually the screw on that trimmer capacitor. You connect it to there, your signal is going to get through both through this cap and through that coil. It's going to get through there, and it's going to go to your grid of that triode, the mixed oscillator, and that's your IF frequency that obviously gets sent through all these filters. There's one. There's the other one. That one there. I think that's the top one. Yeah, that one there. Those two there. Those two there, and that final one is obviously the one that's actually the ratio detector one, the discriminator coil. So we're going to align this as per usual. We decouple critically. So these coils all have a coupling screw, and then they've got the primary and secondary. So we decouple, and then we adjust the primary and secondary as per instructions, and that way we get the whole thing perfectly aligned. Let's have a look at the instructions again. So here we have it. They tell us to set the dial to about 92 megahertz. That's really neither here nor there, but it sets it to the middle of the band, and you have detuned that front end, so very little should come in. And then they tell us to decouple the 501, 503, and critically, then you adjust the primary 501 for a maximum on the voltmeter, and you adjust the secondary 503 so you can null out the microammeter. Now let's look at that guy, that particular filter down here. And fortunately, we've got all that filter down here. There we go. So we decouple that 501, 503. We adjust this one for max voltage and 503 to null out the voltmeter. Then we're going to do the same to this one, and then we're going to do the same to this one. But in this particular case, 401, 402, and 202, 201, this is just to peak the voltmeter. You decouple and you peak, as we can see here. They don't tell us to critically couple it yet. You've critically decoupled, and then you normally critically couple, but they haven't told us to critically couple. That's important because we'll see why in a second. If we go to filter 2, remove the coupling, uncritical, and then you adjust 401, 402 for maximum the voltmeter, repeat if necessary, and then couple them again for the maximum voltage on the voltmeter. Filter 1, remove the coupling or loosen the coupling, and then you adjust 201, 202 for maximum the voltmeter, repeat as necessary, and couple critically again. Then you go back to that first filter 3, and they tell us, well, actually, let me do the first stages first, and then I'll show you what they mean here. This has got to do with the AM rejection. This is pretty neat, the way SABA has done AM rejection on this, and it's a way of balancing that final circuit perfectly so that it does a very good job of acting as a ratio detector, but also as a AM rejection tool for the FM band. Let's get the show on the road. I've got that on 6.75 megahertz coming out. I've got it plugged into the back to the top of the capacitor there, and I'm going to switch it on and look at the voltmeter. And it seems a bit high. It's on the 10 volt range. It's all the way up to 10 volts. So I'm going to give it 6 dB of attenuation. That's brought it down to about 5 volts. I'm going to leave it there. I'm going to give it FM modulation just so that we can hear. So there it is, FM modulation, deviation 25 kilohertz, 600 hertz tone. See if we can hear it. Yes, I can hear it. So that's working. Put that off. We don't need the volume. So the first thing I'm going to do is critically decouple by rotating this counterclockwise. We'll watch the meter. We'll just drop this a bit. Not much, if I recall. That should do it. Now I'm going to adjust this guy till I get a peak on the voltmeter. Let's see how we go. Whoops. It's pretty sensitive there. That's a peak on the voltmeter. That's peaked. Now we're going to move this guy to 0, the microammeter, and I think that's too far down. So I'm going to need the other tool, which is going to be the stick, if I can get it in there. I don't think it's working. I've got to loosen it a bit. Try with that. And I'll just show you the microammeter. I know this is a long view, but guys, take my word for it. It does move, and it is now perfectly centered. And that one is done. Right, let's move on to the next one. So we critically decouple this guy. Okay, then what I'm going to do is I'm going to adjust these other two, that one and that one, for peaks. I will show you the voltmeter as we do it. So let's see what we get here. Trying to get this thing into that screw there. That was pretty much peaked. There's a peak. And the other one. Oh, we've got a nice little bit more there. There it is. Go back to the previous one. There it is. And now I'm going to critically couple it again for a max. That's it there. Okay, another one done. Now we do the same with this. Critically decouple there. Okay, and I'm just going to peak these two guys. I'll watch the meter, and oh, we've got quite a bit. Whoa, got quite a lot out of that one. That's peaked. That's peaked. And now critically couple this one. That's a peak. And that, my friends, is done. And that is basically it. Did that, did that, did that. There's something outstanding on this one, which we need to look at. And that requires a quick look at the instructions again. They tell us to send a 30% amplitude modulated tone on that 6.75 megahertz. And they tell us to couple this one until we get the minimum tone. And the voltage on XY should be about 10 volts. So what do we need to do here? Let's look at this again. We put the volume on. We've got to put modulation, but we've got to put AM modulation. 30% modulation. Okay. And we need to hear a tone. I don't know if I can hear it. Yeah, I can sort of hear it. But they want us to increase the amplitude of this, of the whole signal, till we get about 10 volts on here. This buzz is because we are touching a very sensitive section there. So I'm going to remove that attenuation that I had there. I'm going to increase the signal amplitude just a little bit. It's at 1.4 millivolts RMS there. Just a little bit till we get about 10 volts on there. Okay. And now I need to make sure that I minimize the tone. Now with that buzz, it's a bit difficult to hear it. I'm going to change the modulation tone to 1 kilohertz. Might be easier to hear. Yes, there we go. Now I could put this on a put an AC millivolt meter on the output, but I'm going to do it by ear. So I'm going to critically couple that. There it is. And it goes up, come down. I can't hear it anymore. That is the best it's going to get. And now we do the same thing again. We increase the... Yeah, we've got to play with that one and that one. I can put the volume down now. I've got to do 501 for voltage, which is that guy there. For a max, it was on there. Perfect. And now the other one, the secondary for 0 on the microammeter. It's actually, let me see if I haven't gone, yeah, that's the position. You've got to find the right spot where it goes one way and then the other way, and boom, it's in the middle. There we go. That is zeroed. Okay, good, that's done as well. Now, I've done this really fast, and the reason is explaining it sometimes takes longer than doing it, as you've probably determined by now. But if you want to see a really detailed alignment of exactly this sort of thing, look at the Breisgau one. There are actually 2 videos on the FM alignment of the Breisgau. One of them was a mistake because I had this plugged into the wrong hole in there. So go and look at the Breisgau FM alignment and you'll get a really detailed description on this. And the Breisgau's got 3 IF transformers over here. So there's actually one further step. Anyway, I want to show you something. I'm going to see what the result is of this now after the alignment, because before the alignment, I did a draft of what the response was. Because at the end, what I want to do is do a visual alignment and probably just correct the shape a little bit. So let's have a look at the result of this alignment and see what we've achieved, if anything. Since I had nothing better to do, I decided to plot the curve. And what I did was I literally set it to 6.75, right? I got a voltage measuring 4.58. I left it under 5 because I wanted a common reference. And then I started plotting. I changed the frequency all the way down in 10 kilohertz steps. And I just went all the way down till I got this thing flattened out. And I went all the way up till I got that flattened out. And I found that from 6.75 to 7, so from here to there, 250 kilohertz, you pretty much flatten that out. And here it actually flattens out before that. So this is what we had before we changed anything, okay? And there's something important you can do here. You can take the max and minus 3 dB. You can figure out what that width is there, from there to there. And this is what we get. So if we measure the width from the minus 3 dB points, we get 102 kilohertz. And it's not quite centered on 6.75, this 3 dB point, because the shape of the curve actually starts there. You know, the peak is actually at 6.74 if you look at it here. Okay, but we got 102 kilohertz. It's narrow. It should be, well, probably about 150. Remember that the FM bands are 200 kilohertz apart. So you want this to be fairly wide so you can get good fidelity coming through, good audio. Mind you, with the FM we have on these radios, we're not worried about data or, you know, RDS or anything like that. So it can be quite a bit less than 75 kilohertz either way. But we've got 100 there. It's still too narrow. So what happened after we adjusted, after we realigned, okay, as you've just seen? Well, that's where it gets interesting. What I did is I did exactly the same thing, but I went to the peak and I made sure that I had the peak pretty much where that was so that we get a relative plot, okay? Because once you mess around with it, everything changes. What we want is a relative plot of the resulting curve to the previous curve, to the start curve. And this is the start curve, right? So let's look at the resulting plot. That's what we get. Quite disappointing. Yes, it is. Because you follow the instructions exactly as they give it to you, right? And the result is you've got yourself a curve which is, first of all, it's not centered at 6.75. It's actually centered at 6.76. You've got 10 kilohertz the other way. This one was 10 kilohertz below. But then what you've got it's neither centered, nor is it uniform, nor is it wide enough. It's narrower. So if anything, we've made this situation of this being too narrow worse. How much worse? Well, 25% worse. If you take this and you do the -3 dB point again and you plot down here, it comes to 76 kilohertz. Now that's not good at all, is it? I'm not happy with that at all. So something must be done. So what I'm going to do is I'm going to try a visual plot. Now, the visual alignment on this is very simple. You do exactly the same thing. So I'll center the sweep at 6.75. I'll give it a span of about 200 kilohertz, which would be a typical FM channel. We'll see what kind of plot we get. Now remember, we're expecting this, the green curve, okay? In a slightly different configuration because the span would be less than what we've got here. We've got 250. But anyway, we expect this kind of curve. What are we going to get? My guess is we'll probably get something weirder because that capacitor, that discriminator cap, is actually slowing down the trace. It's acting as a shunt for that trace, and then it acts as a reservoir for the end trace. So as your voltage starts going up, instead of the voltage going up, the current is leading the voltage. So current flows into the capacitor, charges the capacitor. It means your voltage lags. Your voltage gets slowly built up. And then when you get to the other end, instead of the voltage curve following immediately what it should be, it's actually sort of discharging the capacitor. So what we need to do is remove the capacitor, lift the capacitor just temporarily. It'll make a lot more noise. You'll see a lot more noise on the signal, but at least we'll get a better curve. So let's do that and see what it is we get, and then we can compare back to this. What I've got set up here is I've got the capacitor removed from the ground lug, and I've got a clip to ground so that I can just lift it off when I want to. If you look carefully there, this is the leg of that capacitor, the ratio detector cap over here. It's the ground side of it. That's the one that goes to this pin over here, which is ground. So this clip is just being used to connect it to ground over here. It'll just make it easier for me to remove it when I want to show you the effect. I've got the sweep at 700 milliseconds, same as before, very similar to what I did with the AM sweep. And what I'm monitoring on the scope is the top of that same capacitor that I've just mentioned. So one side goes to ground, the other side goes to the one of those diodes in the detector tube. So this is the voltage that appears across that electrolytic capacitor. We'll see that on the scope, and 700 milliseconds. So here we go. That does not look like what we had before, does it? This rising slope here is being slowed down by the capacitor, and the discharge or the drop is also being slowed down by the capacitor. And it becomes more obvious if you take the sweep and make it faster. So if I make the sweep 280 milliseconds and I reduce the time base, it just gets worse, okay? See that? Now let's take it the other way. Let's make it 1.4 seconds and make our time base 100 millivolts per division. Takes a while to acquire. It's sort of starting to look real now, doesn't it? It's starting to look better. Now let's take it one step further. Let's make this, what's the next time base? 200 milliseconds, so 2.8 seconds. Takes a while to trigger, but if I stop it there, okay, we've got our slope. Now if you try and adjust that, it's very difficult. It's getting closer to the center. We know that the peak is actually not on the center, but the slope itself, the whole shape, is getting closer to the center over here. But I'm still a little bit worried about that. I still think it's delayed somewhat. I think everything is shifted to the right somewhat, so we're not getting a real representation. The other thing is, if you try to adjust it, if you try to make any adjustment, it'll take a heck of a long time for you to see the result, which means that you can't really do it in real time. So let's go back to 700 milliseconds. That's fast enough for us to be able to see it. That's the one I think I want to work with. And what I'm going to do is lift that capacitor. Now watch the result on the screen. If I lift, actually I'll remove that. Boom. Much better. Not as easy to see because it's all fuzzy. We don't have the smoothing effect of the capacitor there, but it certainly looks now like it's more real. Now let me just put that back. Got to be careful here that I don't short anything. See that? Take it away. And all we need to do is we can work on this like that, and then all we need to do is remember to put that ground of the capacitor back when we finished. So let me turn this around and let's see what we can do to improve this response curve and also possibly to widen it so that we get a bit more bandwidth. And now we start fiddling. See what happens here. Let's get this out of the way. I don't know what I need to adjust to get this thing better, so I have to fiddle a bit. It's taking it the wrong way. That sort of flattens it out a bit, which is something I do want. There I have actually widened it a little bit. I've made it less sensitive, I know that, because I brought the amplitude down. See, that coupling went up a bit, which is good. If I overcouple, what I do get is a big hump in the middle. I don't mind a small hump, but I don't want a big one. Still haven't done this one here. Mm. Which is the one? This one. I need to get it back that way, I think. think that looks better. I can play a lot more with this, and I will play a lot more with this. Let me just put this, we know this is right on the center. I want to see what that thing looks like. Let me put that at 2.8 seconds again and see what it looks like with the capacitor in place. Of course, here, all it does is it's very slow. We've got our hump in the middle. I don't mind that. It's not a big hump. Of course, we have a triggering problem over there. Let me put the capacitor back in and see what it is we're actually seeing if we do it really, really slowly and capture one of those waveforms. Try to do this live. I think I've got it, but let's freeze that. Okay, this is what we've got. It's, again, forget about the fact that it's shifted slightly to the right. That looks pretty good, actually. That is probably the best you're going to expect. I would have liked a flatter curve at the top, but this might actually make it easier for the automatic to work. Obviously, I haven't played with the automatic yet. But yeah, that's what we've got. You see what I mean by removing that capacitor? It makes a heck of a difference. Good. All right, folks, I did some tweaking around there. Remember, I had actually adjusted the curve by touching the one that I shouldn't have, the secondary of the last IF transformer. That's the one for balancing. I should not have messed with that. So what I did is I went back, corrected that, and then I got this curve. And the way I did it is the same as I did before. I looked for the maximum point, which was, you know, here, 455 or 4.58. The maximum here was 4.46 or something. I got them approximately at the same level so that I could get a relative response and be able to compare to see what it is that I had, you know, before and how it improved. So here we have the three curves, and it's pretty obvious. That one there is the original curve that we had. And we don't need to look at that anymore, so we can hide that one. Then we were left with these two. That was the this green one. Why did it change color on me? Doesn't matter. This one here is the one that that resulted from adjusting just with the voltage levels without doing a visual alignment. And this one here is the one that resulted from my final tweaking. Damn, I'm getting anal. Anyway, looks better this way. So this is the curve that we've got, and this is measured by the same method that I used before, literally altering the frequency by 10 kilohertz at a time and measuring the voltage across that capacitor and then plotting it, and this is what we've got. And what we have, as you can see, between here and there, since the peak is approximately the same, this is our 3 dB point, and we've widened it. Now, it might seem that we've widened a heck of a lot. We haven't really widened that much. In fact, if you look at this with the bandwidths marked in, this is really what we've got. We've got the original one, that's the blue one. There we go, that one there. That one had 102 kilohertz of bandwidth originally. The green one, which is the one that I adjusted with the meters, had 76 kilohertz of bandwidth, so it dropped it. And now our red one has got 110. That's what we're left with, 110 kilohertz of bandwidth. Now, you could actually make this wider if you drop the peak some more. It just means that you are increasing the bandwidth, but you are reducing the sensitivity. Now, bear in mind that this radio is mono FM. Unless my theory is completely gone, the first 15 kilohertz of the signal is actually where the mono FM signal is transmitted. When we talk about having, you know, 75 either way, that's so that you can fit in the left plus right, which comes first. Then there's the pilot tone, then there's the left minus right, and then you've got a whole lot of other bandwidth that you use for RDS systems and traffic notifications and all that sort of jazz. We don't need that. So this is more than wide enough for good fidelity sound to come through. And I'm happy with the result. That little bump there, that's neither here nor there. You'll always get something like this. If you can get a curve that's exactly flat at the top and exactly the same height, you've cheated. I don't want to cheat. So that's what we've got. And what I've done is I've gone the next step and I aligned the FM motor. And basically you do exactly the same steps. You follow the same steps as with the AM. What happened was I was filming it and I wasn't recording and I wasn't ready to go and take two. I very, very seldom do take twos on my videos. It either comes out or I admit that I messed up. So the result is we've got this FM completed. This is the IF passband. The motor's been aligned. I now want to show you what the result is of that motor. It is working. It's not as fast as I would have wanted it to be, but I think that's probably systemic. It seems to be the same way with the AM, and I'm not going to mess with that. I like the result. So let's have a look and see what the result of this tampering is. Here's something else I want to show you. I took that screenshot of the final result that I achieved. This is the curve that I got. I did this with the capacitor in place, and I did this over, I think it was 7 seconds or 14 seconds or something like that. So a really slow sweep. And I want to show you what happens when you superimpose the plot that I've just shown you and tweak it a little bit to get it to the right height. Now this is exactly the same dimension width-wise. I've just tweaked it down. In other words, I've brought it down so we get the same sort of maximum amplitude over there. And that is a pretty good correlation. I mean, look at that. And you can clearly see, you see, this is the center of the sweep that we have below. And if I take the center of this sweep, which is that line over there, and I put it there, in fact, I can get it exactly right. This is what we get. In other words, what's happening is that the sweep is being delayed. Watch, if I move that across, that is pretty close, right? That's real close. We finally see theory actually correspond to the measured result. It's always nice. All right, let me do a test and show you the result. Okay, let's test this thing. FM. I can't leave it on music for much, but this is pretty good. That's one of the stations I pick up perfectly. This one is one that I normally almost don't pick up. These are stations, I get 3 good stations where I am. When I say good, I mean perfect FM. That's one there. The other one is actually at 101.6, which I can't reach with this dial range. I'm going to make an adjustment to extend it when I do the RF alignment. But we get a few more around here, which are usually pretty weak, but this is not bad at all. There's a little bit of hiss, but that's normal for this station where I am right now. That's the other one that's pretty strong, but again, I can't play that because that is music. And let's try the automatic. I'll put auto on. It's picking up even the weaker stations. So that is working as expected. And it works the other way as well. So that's it. That's it. Our FM is working pretty well. So the next step will be the RF alignment for the AM and the FM. What I want to do here is the full RF alignment. I'll check all the alignments on the AM bands, check the FM, show you how I do that. Also, what I want to do is something I've done on quite a few of these radios. The ones that go to 100, I want them to go to 101.6, which is one of my favorite stations. So what I normally do is I adjust the, when I do the RF alignment for the FM, I extend the band a little bit to the right. Usually the bottom end, 88, stays the same. I've got a station on 88, which I sometimes listen to, not much, but I want it to be able to pick up. And the end one will be slightly stretched, which means that our dial perfection will not be there, but at least this radio will pick up the one station that I always listen to. 101.6 is where I normally tune my radios to, and most of these radios need a little bit of tweaking just to extend the band a little bit. It's fairly easy. You'll see how I do it. I've done it before. And for now, I'm going to leave you and start working on that. So I hope you've enjoyed this. And if you have, click like, share, subscribe, and all that jazz. And if you want to support the channel directly, you can do so on Patreon and PayPal. Once again, thanks for watching. Bye for now and stay safe.